All right, well, welcome everyone. If you didn't attend yesterday, I'll introduce myself again. I'm Dan Boschen, of course, and I am a hardware design engineer. My experience is mostly, most of my career I spent on wireless systems, components, and complete radios. Everything from basically the PHY layer, everything from the antenna to the baseband modem, both in the analog and digital domains. I have experience in both areas. Up to 60 gigahertz carrier frequencies, so working in those areas. And now as of present, I'm working for Microchip in Beverly, Massachusetts, working on atomic clocks. So a little different. A lot of things are close. There's a lot of control loops in atomic clocks, so that's where, and there's a lot of control loops in receivers, so that's where I bridge the benefit there. But most of where I might play now is more in system design in those areas. So I'd be like, what's the optimum
loop bandwidth for a carrier tracking loop to what's the noise figure of an FIR filter, for example. So in terms of looking at that cross perspective digital. So you'll see some of that today. So if you have a digital background, you'll connect with getting introduced to the analog. If you have an analog background, you'll connect getting introduced to the digital, the same thing. You see it both ways. So with that, we're going to talk about control systems. And what you're going to see, this is going to be the crash course in control systems. So they have been exposed to it slightly before. You're going to get the deep dive. You're going to get what I think is the best way I can possibly explain it to you in 2 hours. And it's going to be the part of control system theory that's very applicable to receivers. So in the design of carrier tracking loops, like I mentioned, or time recovery, or AGC, or power control loops, this will all be very practical for that purpose. And then you're going to see how to use Python for doing it, but it's not all about the Python. If you're not a Python user, what you're going to see is also applicable to MATLAB and Octave if you're experienced with those things. So you'll see a lot of similarities that's going to be very practical. And this is cool. I used to teach courses. I do it online now. I used to teach for the IEEE in a hotel conference room. It would look just like this. So this is such a great memory for me from those pre-COVID days. We actually went to a conference room and did that. I love to see the faces. Everyone turns off their camera when I do it online. And I can read the room to see if I'm totally boring you or if I can say that in a different way. And with that, we're still small enough in here that if you have questions as I'm going through it, we have plenty of time, as long as you want to stay here that long. So if you have questions on a particular slide as I'm going through it, feel free to interrupt, raise your hand at that moment, because it may help your understanding of the subsequent slides and help others as well. And I love the fact that you're all here. What I tell people that take my course is that nobody else I know lets you talk about this stuff for 3 hours straight. So my wife's sick of it. My kids are sick of it. My neighbors jump in their house when I step outside, but you guys are here and we can talk about some really cool stuff that I think is cool. So I'm glad you want to hear it. So first, we'll just cover some examples. These are just high-level examples to give it some context as to what the heck we're talking about. So here is the first example is this integer n phase lock loop. Integer n phase lock loop. And what you're seeing is a reference oscillator that could typically be a lower frequency, as I'm showing here with this divide by n that you're going to see, that is, has much better spectral purity than some high frequency VCO, voltage controlled oscillator. So as an analog component, there's a voltage, it controls the output frequency. And we're going to take that output frequency and we have a frequency divider that's going to divide it down so that it matches the same frequency as the reference oscillator. And then we use a phase detector that's going to measure the phase between those two inputs, and that's going to give us an error signal. Ideally, we want 0 error. And that'll go into our magic loop filter, and the loop filter's job is to float up to the value it needs to be to make that error 0. So that's the integer n phase lock loop. And with it, we can change n, and that will step the output within the step size given by that reference oscillator. So it's an integer n PLL. Similarly, here's a frequency lock. So the difference between a frequency lock loop and a phase lock loop is what are you using as a discriminator? What are you using as your error detector? If it's converting frequency error to some error signal, then it's a frequency lock loop, no matter what order you make the loop, et cetera. So here we have something called a frequency discriminator. It's going to take the output, and instead of looking at phase, it's looking at frequency. It's going to produce a signal, a DC signal proportional to the frequency of the VCO. And then we have something that's taking the difference. And here it's just a set frequency. So if the voltage out matches the set frequency, we get that beautiful zero error again. And then we have our magic loop filter that's going to float this control voltage to whatever it needs to be to guarantee we have zero error. And then here, we're just going to keep adding more complexity. Right? So this is a mixed signal power control loop. Mixed signal. So to explain these components that you're seeing, above the dash line is an analog system. And we have a voltage variable amplifier. You might also see it as a VGA, variable gain amplifier. But there's a control voltage, and it's going to vary the gain. And we have an input power that's getting varied. And then we have the PA, a power amplifier. And then we'll couple the output, and we'll have some detector that'll convert output power to a voltage proportionally. So that's our discriminator, our power discriminator, right? So we have a power control loop because we're using a power discriminator. And the SPI, ADC, and DAC, so those are analog to digital converters, serial aerial analog to digital converters. So we're getting now a digital representation of the voltage that represents our power, right? And then same thing. So we're going to subtract it from a set point. If it matches, we have zero error. And all this stuff in here, you're going to see more later. That's our loop filter, our magic loop filter that's going to float this digital value to what it needs to be, DAC, converting it to analog so that we have zero error. So it's setting the output power. Someone say something? Setting the output power based on, in this case, a mixed signal design. Now here, don't get too scared. We're not going to dive into all this, but it's a motivating example. In fact, this is something that is covered in this DSP for software radio course. So if you see my courses, this is the full detail of that, where we have 15 hours to talk about it, not 2. But what you see on the left, this is really cool. This is why I love DSP, because if you look at it, it's just a bunch of multipliers, add, delays, and lookup tables. So that's some simple components that we can piece together in exotic ways to make really cool things. So that is a decision-directed carrier recovery loop. And what's really cool about this, and what you're going to see today, not for this specific one, but you're going to see the techniques that lead to this, is this whole thing with all of its complexity is reduced to this one equation in ways that we can then from that see how it responds versus a time-based sample-by-sample simulation. We can see how it steps from one frequency to another, or how it converges, its lock time, its bandwidth, and all the considerations we would actually have on what do we need to configure and what does it matter to us in our receiver implementation. But it's really cool that it's all in this one line that we'll implement with 3 lines in Python to get the results we'll see. So to show you that, the background of that, there's a simulation I did. So a simulation I did showing, hey, we have, in this case, it's QPSK. So you're seeing QPSK, and you're seeing all the transitions from symbol to symbol as it changes from one symbol to the next, all the possible transitions that you're seeing at IQ baseband. That's what you're seeing in terms of the constellation. And then there's a frequency offset, so a carrier offset, a frequency error between what was transmitted and what was received, which will inevitably happen due to Doppler or that we're just running on different clocks. We can't avoid it. So it takes this nice square thing that we could demodulate and spins it. So that's what you're seeing. You're seeing it spin at that frequency offset rate. Make sense? And here, if there's a question about this, it's a good time to ask, because I'd like to know that it's clear to everybody.
Good. So is that frequency offset programmed in, or is that just inherent to
Yeah, so it would be, in real life, it would be just that transmitter has its own clock, I have my own clock. Even if we weren't moving, there will be a frequency offset. We can't be exactly in the same frequency. And then there's Doppler when we start moving. In my simulation, I programmed it in. I'd made a simulation of it. So here it's showing it how it actually works and how quickly it did converge. Quickly is relative to 55 kilohertz offset. So this was all completely within the capture range of the loop, right? The capture range of the loop where the loop model will still work and predict the linear operation. And it's stepping. So you're seeing it actually work from this offset in time versus based on number of symbols, and is stepped and converged exactly to the 55 kilohertz offset. And we're seeing what the final result looks like, ignoring the acquisition samples. So these first samples when we transition, I chopped off so you could see what this receiver looked like after we removed the spin and after it went through the receiver. So as a side note, what you see here, if you're familiar with this, what you're seeing here is what the root raised cosine filter looks like at the transmitter, passes through another root raised cosine filter in the receiver. I'm only saying that if you've seen that before, we're not going to get into it, but that's why you see tiny dots here. These little pretty dots. OEBL. So that's pretty cool. And this is really cool because what you see on the left is the results of my time-based sample-by-sample simulation matching exactly what we would expect to see in the digital receiver, right? Matching exactly what you would see sample by sample, which is good to do. It's going to capture all the nonlinear effects, other things that the loop model won't capture, but it's showing the result of that equation in these 4 lines of code here. And this is what you're going to see in more detail, how it's matching it pretty much exactly in terms of its step right through the 0.5 and doing it. It's the exact prediction, meaning the model was done well in terms of using the actual parameters that I would expect in the implementation, and just really cool that we could reduce it to this, and then we can predict things like this response time, step time, impulse response, and bandwidth, all that stuff very well and very quickly versus the time and complexity to make this model, which I ultimately would do for verification to the digital system. I'd ultimately have that, 3 or 4 weeks into the project. But on the first day, after the first 15 minutes with a napkin, I can get to that quickly, which is very cool. So that's what we're going to do. That's why you're here. We're going to see how to do that, not with the carrier tracking loop, but we'll go through some example analog PLL and digital PLLs to demonstrate this. So first, I'm going to drag you through some fundamentals in terms of getting your head around, make sure your head around there are some important concepts. Somehow I'm going to have to get you on the speed on what the Laplace and Z transform are very quickly. So we'll give it a shot. And first of all, the way I teach this stuff, I always start with this. I don't start with sines and cosines. I think that ultimately confuses everyone, and I have lots of reasons why. And to get your head around the spinning phasor. Spinning phasor representing a single tone and frequency. And the idea of this, when you see this math, if you haven't seen it for a while, it's just magnitude K, angle phi. That's all it is. E to the J phi, magnitude 1, angle phi. So we're going to have, your I and Q are real and imaginary axis, and we have this as a representation of having a magnitude. It's a phasor, and here's the angle relative to the real axis. So when we have these complex signals, so I love complex signals, it makes our life a lot easier. There's lots of notes you see out there, white papers like Rick Lyon's complex is not complicated, all that kind of stuff. And it's not. It's there to make our life easier, and it does. So come on in and do that with me. And if your head is trying to bring it back to sines and cosines to explain it to yourself, you're still on the other side asking for trouble, and I'm going to show you why. So we could have magnitude changes with time, right? So this is the magnitude is a function that's changing with time, and the phase rotation there, the phase rotation is fixed for all the waveforms. So it's just a rotation, and the magnitude is changing. So that would be an AM modulation, right? Or we could have phase changing with time. So the magnitude's fixed for all time, and the phase is now a function of time. So that's phase modulation. Or we can do both. That would be QAM, for example, quadrature amplitude modulation, where we're changing both magnitude and phase with time in this representation. And importantly, this magnitude and phase and complex representation of a waveform, it could be any function. We're doing functions versus time, but it can be a function versus frequency. That would be a frequency response of a filter, for example. So every sample has magnitude and phase. Every sample has magnitude and phase. So don't think of phase. If you picture that image of when it's first introduced to you as here's a sine wave and here's another sine wave, that's a time delay. It's not a phase shift, it's a time delay. That horizontal axis is time, that's a time delay. And it really can mess you up if you associate it directly with phase. Phase is a rotation on a complex plane, and that's it. And then we can explain how we can map a time delay to phase and stuff like that. But there's a lot of paths that get confusing, especially when we get to carrier recovery and timing recovery. Two separate things in the receiver. One works on phase, the other one works on time. Two independent operations. And so that's an important takeaway. So here, the whole idea of positive and negative frequency that confuses many. Positive, negative frequency. So you start with this sine wave or cosine wave that I have specifically here, and then our great Fourier transform that represents it into two impulses in the frequency domain. That's the Fourier transform of a cosine wave. You see two impulses. So what I see is two tones, two frequencies. So the cosine wave contains two tones. And each one of those tones is the spinning phasor. Each one of those tones is the spinning phasor. So you have, this is Euler's formula, if you've seen it. The cosine omega t is e to the j omega 1 t plus e to minus j omega t over 2. I just put the 2 up there to clean it up. So what is that saying? What is that saying? Oh, okay. A cosine wave that's completely real. This is completely real. The whole Fourier series expansion, the whole Fourier transform, the Fourier series expansion, it's decomposing an arbitrary waveform into a bunch of e to the j omega t's, not a bunch of cosines and sines. It's more confusing. Each one is e to the j omega t. Each impulse that you see on the frequency axis, every one of those represents a single spinning phasor in the time domain. So it's twice as much work to convert it to cosines, and now you got twice as many that you're dealing with instead of the fundamental component is needed to j omega t. So that's kind of cool. We see this here on the cosine wave versus time. This is another way that we can view a time domain waveform on an IQ plane, right? So we play time forward, and the dot, that's the sum of these two phasors would land here, and it just moves back and forth on the real axis. That's how we would see it if this was playing forward in time. Just another way to represent it, but very handy. And I decomposed it into each one of those components. So this one that's negative frequency, e to the minus j omega 1 t, right here is rotating. It's the phasor rotating clockwise, and that's in the time domain. The Fourier transform of that alone is a single impulse in frequency. So you rotate in one domain, it shifts you in the other domain. So that works in both directions. That's how you work with phase. So we have two of them. Then we have one that's rotating counterclockwise. That's the positive frequency. So think of frequency as bicycle wheels, and now we can tap direction. Now we can tap positive, negative. Does that make sense? Is that helpful? Is there confusion still? I like to hear what the confusion is. So the other thing I hear too a lot is that, complex signals don't actually exist in the real world, right? Now we're conflating real and imaginary. And I figured out finally it was René Descartes that coined imaginary back in 1637, I think, in terms of as a derogatory explanation of these mythical imaginary numbers. But it's, the fact that that's imaginary and that's real has been a struggle for me in terms of why are we naming that way. So imaginary numbers, real numbers, they're all equally are abstraction to describe the physical world, right? So there's not like one exists and more than the other. And imaginary numbers and complex numbers is an ordered pair of real numbers. That's it. Whether you use it on paper, right? I plus JQ, you're doing your analysis and you use I and JQ, or you break it into cosine and sine components to figure out the I and the Q, or you use it represented as magnitude and phase, which is that K to J. Each of these uses two real numbers to represent the complex number. So every complex sample is an ordered pair of real numbers. And so the way I visualize it when I'm thinking of these things in my head and getting to the intuition, or when I'm doing the analysis on paper, I'm completely treating each complex sample as a single number. So the e to the j theta is great as a representation of it and makes life a lot easier. So, and then when I finally get done and the whole block diagram collapses down to its simplest form, I'm able to do that way, and I go to build it, then I will break that out into its I and Q components to build it. But again, you have in the labs, there on the table, two data paths, I and JQ. I see it as one data path. Yes, you need two scope probes to measure the complex waveform, but doesn't mean it's two separate waveforms. It's one waveform, right? One waveform. So I see this as one data path instead of trying to imagine it as two, and it makes life a lot easier. Here's a motivation for that. If you try to explain how a full complex multiplier can be used to shift frequency, and ultimately, if you're trying to explain or introduce yourself to single sideband modulation, and if those explanations lead you to the cosine, cosine, sine, sine product rules, that's what's on the right-hand side. That's the implementation. But the understanding of it is you're just multiplying the single complex number with another, the single complex waveform. And look at that, e to the j omega 1t. So at this point, when I say magnitude A, e to the j omega 1t, I want you to visualize, okay, it's a single spinning phasor at frequency omega 1, right? Is it a positive or negative frequency? Not both. If omega 1 is positive, it's a single spinning phasor. So the cosine has two tones. This is one tone. Where would you see it on the spectrum? On the positive side, omega 1. Single impulse there at omega 1. It's that easy. And now if I create another one, e to the j omega delta, just some small frequency offset, and I multiply it with a single complex multiplier, so I see one multiplier, then you're just adding the exponents. We're done. I'm done explaining. Look, it shifted the frequency. Very easy. And then, of course, when you're detailing all this in the single sideband modulator and getting down to implementation, you can then ask, hey, is that frequency, single frequency, or the modulated waveform high enough that I can take the real part, which creates the negative image, now it's back to a cosine, and it pops up. They don't overlap, you're safe to do it. If they overlap, you can't, and that's why we need complex I and Q if they overlap, if that matters. So then we go to implement this thing, and yes, a full complex multiplier requires 4 real multipliers and 2 adders, and then we get to the implementation, but I'm not thinking that way to understand it, process it, or even explain it, right? It's much easier. So, not sure how this got in here, but my neighbors have a flock of chickens. My wife looks out the back window. Sometimes they get in our backyard, and she says, look, there's a couple chickens in the backyard. I look out and I say, oh, I see one complex chicken. That decision-directed carrier recovery loop. I mean, this is pretty wild when you look at it without further explanation. Like, wow, we're actually making something with all these add and delays and all that type of stuff, and I'll put blocks around it to give it some more detail as to what it is. And you're starting to see some of those structures we already explained. There's the phase rotator. There's that single multiplier, right? That same phase rotator or complex multiplier. We have I and Q coming in, and we multiply it by an IQ signal. It's shifting the carrier, and we'll have this phase detector, and then there's that loop filter. We'll have an error signal. There's the loop filter. It's going to float to what value it needs to be, and this is a numerically controlled oscillator. It's the digital equivalent of the VCO I showed you earlier. So we don't need to understand all that. I just wanted to show you this again, because if I redraw that into single complex data paths, and that's how I make my diagrams. I'll draw the complex paths thicker than the real paths, but this just is a lot easier for me to dive into and understand, as long as I'm not trying to force the e to the j and the t back to cosines and sines again in my head. It's just very, very intuitive, and it would be if you allowed me to explain each of these blocks and we talk about it, and that's in that other course where that becomes simpler. And it's beautiful in its simplicity. So let's dive into Fourier and Laplace. So these two French dudes, Fourier and Laplace. Anyone from France here? No one? Yes? No? Do you know anyone from France? No? Fourier. So we have them to thank for Fourier and Laplace. And anybody from Germany here? Yes. Okay. So we have, so who do we have? Yep. Hilbert. Yeah, I'm thinking of the Hilbert transform. So here's the Fourier and Laplace transform. I say we because I have German relatives, but I probably have French relatives too. So I can't really say we. I'm not German, but so Fourier and Laplace. So the Fourier and Laplace transform. So first of all, what you're seeing here on the right with this complicated math, okay? You're seeing a product of two functions, and then we integrate the result. Okay, this multiply and integrate shows up again and again and again in BST. It's a correlation or a mapping. I like to view it as a correlation. It makes a lot of sense out of it. So you may see it, and this is continuous time and discrete time. It's multiply and accumulate. Multiply and accumulate is a correlation, the same thing. So with it, what are we able to do? We can take some arbitrary function, x of t, whatever it may be, that we know little about. We just have the data, right? And we can set omega to some value. That's setting it to a certain frequency. Set omega to some value. And then what is it? We're multiplying that function with e to the minus j omega t, with a spinning phasor. Right? So we're seeing our spinning phasor again. We see these all over the place. So we multiply it with a spinning phasor. And the process of doing that, if this x of t is exactly the complex conjugate of that, then it's spinning exactly the opposite way. It keeps landing on a real axis, and then we accumulate, and it grows to very big numbers. That's correlation. That's correlation. The noise in it will go down the longer we look, and the signal goes up. So we're correlating each frequency. That's the Fourier transform. It's like take x of t, and then with lots of computations, the way it's shown here, because we have to set omega to each value, and then, okay, with omega at this particular value, do all this multiply and accumulate or multiply and integrate, and give me the answer and put that one dot on your frequency axis. Now move to the next frequency and move to the next frequency. In the end, we swept all the frequencies and we determined a correlation to each frequency within our waveform. So that's pretty cool. That's the Fourier transform. So Laplace does that as well, except he's correlating to e to the minus st. Same thing, he's correlating e to the minus st. So what is S? What is S? So S is a complex variable. Sounds complicated when we say that. We typically see it as sigma plus j omega to give it some good abbreviations. I could have said I plus jq again, right? It's a real and imaginary part. And it represents, so e to the minus st in the Laplace transform, if we substitute what S is into its real and imaginary components, and we can separate out the two in the product, we're getting a real e to the minus 5t. Can anybody picture what that looks like? E to the minus 5t, just an exponential decay. Simple, right? exponential decay. So we're pulling out the ability to decay or grow in time times our friend now, the spinning phasor, right? So if sigma was zero, and I take the real part just so I could graph it on one graph, that's all, instead of trying to show you a spiral, then we're seeing the real part of, which is the cosine, the real part of e to the minus j omega t, right? If S was only complex, if sigma was zero. So here I put in some actual values for omega, and we get a frequency. So what I want you to see is when S is just imaginary, it's a spinning phasor with constant magnitude. And then if we add in this real component, we can allow it to decay or grow with time. Right? So the whole S and Z plane, is showing us the result we would get in the S plane. That's all you've seen so far. Is the result we would get if we varied all possible S's and did that correlation we talked about. So because S has two knobs, the real axis and the imaginary axis, we have a plane, right? We have a plane, and it's showing us the result we would get. These are all the possible things we could correlate to depending on which S we pick. That makes sense? And its use specifically will be for decomposing an arbitrary time domain function into these individual frequency components. And yes, this is a frequency. It's something changing with time. It's a frequency. That would be a real frequency as a decay, or an imaginary frequency as a rotation. Both frequencies. So the S plane, this is the S plane. If I graph the magnitude of that result, so that's us going to each one of these possible S's and seeing what we get, and the results will have both magnitude and phase. So you're not seeing phase here, but phase is also very important. So you're just seeing the magnitude. So imagine if I had this particular function, and if we restrict S to be the imaginary axis, then it's e to the j omega. We're back to the Fourier transform, right? We're back to the Fourier transform. Between the two, here, if S was minus j omega, these would be the same. Other than starting, and also assuming the function's causal. Let me say that, because this starts at time zero. Okay? So you see that here in this example. If we just restricted, here's this whole surface where it has a magnitude, and if we restricted S to just be the j omega axis, it would go across this line here. There I'm plotting it by itself. You're seeing a frequency response of a low-pass filter. Okay?
What the real axis represent?
The real axis represents decay. Yeah, so we have, this is something on a real axis and it's decaying. And again, this result that you see as the magnitude is saying, hey, you had some time domain function. For that time domain function, whatever you created, I want to decompose it into these elements, spinning phasors with growth and decay. And that, so you answer this, that time domain function specifically for all our use here, and typical use will be the impulse response of a system. It's not the input to the system, it's the impulse response of the system. That's where we're going to use this to be most useful. You have some time domain function that's the filter. You give it an impulse and it kicks out. Okay. So what if I gave a filter? What if that could be the impulse response of the filter right here? So I could have, that's a low pass filter where I kick in an impulse and it coughs out that thing you're seeing on the right. This is ripple decay. Right? That's the impulse response. So if I said, what's the Laplace transform of that, is like, hey, how would you describe this if I just said how many components of E, it's already in that form, e to the minus 0.5t with the j omega, whatever j omega I use. So when you saw the results of that in the S-plane, you would see a pole right at that omega is the minus 0.5 and the j omega 2. You'd see two poles on the left half plane representing that. That's what we needed to represent it. Or in this case, it'd be a single pole. I'm sorry, there's only one fundamental component. If it was a cosine, you'd see the two of them. Let me show you another example that shows that. Here's a specific one. If this was the impulse response of a filter, e to the minus 2t, so I give it an impulse, costs out this decay, just like I'm showing there. That's the result. This is a low pass. It's a very simple first order low pass filter. Okay. If it did that, I take the Laplace transform of that. This is how it would look, or this is how we would hand it to each other, because I only have to tell you where the poles and zeros are, because every other point on here is defined exactly by where that pole is. That's all we need to know. It's easier for me to hit that both are those three graphics, but I'm giving you that same result. So this is saying, hey, we have a pole at s equals minus 2. Why? The pole is where that goes to infinity. So if you think about it again as a correlation, right? If our function itself in time is e to the minus 2t, and then we go through and we try every possible value and we put it into the Laplace transform function, right, which is correlating to x of t. When we set s to be minus 2, you'll see that function will go to infinity, will explode, right? And that tells you, I look at that and I say, oh, your function is e to the minus 2t because that's the s where it made the pole. So every pole that you see is revealing to you what that function is in terms of these fundamental growing and decaying spinning phases. Okay, that's enough to know about what the S-plane is, as long as you guys get that. If there's any question on that before I move on? Actually, I think I have one more example. So you can't get away from it. Yeah. Here is this is the function we were talking about before if it was a cosine. So this would be, if those poles are right on the j omega axis, you're seeing the cosine we first introduced, two impulses right on the omega axis. We shift it into the left half plane, it just means it's decaying, and that's why it's stable. So the time domain function would be a decaying cosine in this case, right? Which is e to the j omega plus t plus e to the j minus t. So you're seeing those two e to the j omegas plus their decay, which is given by the real function there. So the plot here is the surface plot of the magnitude. And again, you see, hey, once we have this whole thing, which is given to us this way, we just see the poles, like 10 poles going up to infinity. And if we stuck with just saying, I want to sweep S to just stay on the j omega axis, we're getting the Fourier transform. So the magnitude of that surface when we stay on this axis, which is this red that I plotted here, and I'm showing it up there, that's the Fourier transform. That would be the frequency response of this low-pass filter. See. So this is a second-order low-pass filter. If you plotted it on a log scale, dB and dB frequency, it would look like a traditional low-pass filter you might have seen with some slight peaking coming down, 40 dB per decade as it's dropping. That is what you're seeing here, given by the two poles, given by the denominator. If you multiplied it out, it's s squared, so it's second order. So Fourier and Laplace, as I introduced, was the continuous time. So the continuous time waveform in the analog waveform. If we go discrete, integrations become summations, right? So a moving summation and adding an accumulator, that's an integration, a digital integrator. So we're accumulating. So this is saying, hey, we're going to sum every result, every product. That's the multiply and accumulate I was referring to. Set n, whatever n is, multiply it by this spinning phasor as we increment n. That's going to be rotating, right? Multiply it, add it up for each frequency. It's the same thing we talked about before, so integrate, summing the plots, right? And we can do that with Laplace as well. So this is a discrete time Laplace transform. We just replace the integration with summations, and t becomes n capital T, typical. We want to keep time in seconds. Little t would become n capital T. And then if we say, hey, let's just talk in sample, it's going to be a lot easier. And capital T, one sample. And you see this form right here, x of n e to the minus Sn. So the cool thing is Mr. Z, whoever that was, someone from Bode Labs, I actually can't remember who it was, because they made it the Z transformer instead of Fourier and Laplace, did this substitution. So we're going to substitute, instead of having to deal with this exponential, because of the repetition that we're dealing with, this will actually work. We're going to substitute z e to the s. So e to the s is going to be substituted with z. That's all. So we swap that in, and then this equation becomes immensely simple. It's just x of n, z to the minus n. That's the z transform. That's the z transform. This upper one is, by the way, the discrete time Fourier transform that I talked about more yesterday, the filter workshop. But the discrete time Fourier transform is continuous in frequency, and that's how for discrete systems you would get a frequency response, not the FFT, which is individual points in frequency. We want a continuous frequency response. Even though it's digital, doesn't mean we can't have any frequency that we sample in the time domain, right? So we want to know the frequency response for any frequency coming in that was sampled at the sampling rate. So that's the DTFT. So you can do that by zero padding in an FFT, get the samples on the DTFT, but that's it. It's saying n is going from minus infinity to infinity, as opposed to the FFT where we restrict n to be 0 to n minus 1. I'll tie those together. So this z e to the s, so we did this substitution. We take every e to the s, for every value of s, we take the inverse log of it basically to get a value of z instead. So this gives you the mapping from the s plane, which we see on the left, to the z plane, where if s was the j omega axis, which we should recognize that's the Fourier transform. We want the Fourier transform, restrict s to be the j omega axis. So how does that map over? Well, if z is e to the j omega, because s is just j omega, there's our friend again, right? It has a magnitude 1 and a phase that's changing, in this case with frequency. So it's the unit circle. So when you see the z-plane and you see this unit circle, that's the same thing as the j omega axis. So anything we know about that or learn about that, for example, one thing you'll learn as you do more of this is those poles, if they get closer and closer to that j omega axis, that represents a high resonance, right? And you can kind of picture it. That pole was a tent pole, right? If we get closer and closer to the j omega axis, was our frequency response, well, then our frequency is going to go way up, right? So the same thing. So it's the same thing you'll see here as we deal with poles and zeros inside here. As they get closer and closer to the unit circle, there's higher Q resonances. A good takeaway in terms of that. Also, you'll learn with control systems that we're talking about is poles in the left half plane is stable. So if you have poles in the left half plane, it's stable. If it's in the right half plane, it's not stable for causal systems, right? Causal systems. So that left half plane maps to inside the unit circle. So now you have discrete spinning phasors decaying with time that would be represented by the points here. Same way the S-plane represented spinning phasors growing and decaying. And then the real axis, and this is just doing the substitution, the real axis is that goes from plus or minus infinity is going to go to plus infinity and go to 0 on the z-plane. So 0 is how negative infinity on the real axis would map to the z-plane. Make sense? So it's a logarithmic scale that you'll see on the real axis. So these grid lines are going. And then finally, this origin this origin where S is 0, if you think of the Fourier transform again, what does that represent? What is the origin as far as the Fourier transform? When I have omega equals 0, DC, right? Nothing to do with current. We just call it DC. But DC is one of those waveforms with time that just doesn't change. DC can have phase. And then here, that point maps to Z equals 1. So as you start getting used to doing things in S or Z, mappings are very handy to provide and saying that, okay, that's the same thing as there, going in between them. And that helps with mixed signal systems and things like that. Any questions or comments? And that's showing the, if this part of the Cartesian graph here would be these polar radial things going out, and you can kind of see how the whole left half plane can come in. So this particular mapping that I showed you is it's called the matched Z mapping. There are several different mappings. They all have different advantages and disadvantages. The big thing is there is not a mapping that exists that preserves both the time and frequency characteristics of our continuous time system. So it's, what do you want more? Do you want to match the impulse exactly? That would be something called impulse invariance. Or do you want to match the frequency response exactly? Or do you want to match neither, which is this matched Z transform? Gets you close on both, but they're both in error. So that's a consideration between all the different mappings that exist that we'll touch on. So Z to the minus 1, the Z to the minus 1 block that we see everywhere in DST block diagrams represents the Z transform of a unit sample delay. So when you see it in a block, it just means you delayed one sample of the sampling clock. So it could be, a flip-flop register that's taking the input, or a bunch of them taking the input data path. A clock goes, and now it goes to the output. That's one sample delay. That would be Z to the minus 1. So what you're seeing here, this is the Laplace transform for a constant time delay, x of t minus t. If you look that up, you would see it's this. And as far as a frequency response, of a sample time delay, if I want the frequency response, I replace S with j omega, right? So if I had a delay of t samples, the frequency response is e to the minus j omega capital T. What do you observe about that? Again, e to the minus j omega capital T. It's a phase, yeah, and what's the phase dependent on? Yes, it's a phase that's dependent on frequency. So for those RF folks like me that played on a network analyzer, you would immediately recognize this. For the rest of you may not. But if you had a length of cable with a fixed time delay, and you measured S21 phase, you would see it would look just like this. It'd be a linear phase going down. The intuition there, imagine it's like the cable, and I can put in a low frequency sine wave or a high frequency sine wave at the input. And you compare the output that you get with that. With the low frequency sine wave, it's a fixed time delay. We didn't change the time delay. But that mapping of phase from the sine wave is being the time delay between the input and output, right? The phase divided by 2 pi of the whole sine wave. It's going to be very small for the low frequency sine wave. And then as I keep increasing the frequency of the sine wave, if I compare the input to output for that same delay, there's going to be a lot more cycles potentially between input and output. You're going to see the phase gradually increase as I increase the frequency. Make sense? So here, if we have one sample, it's z to the minus 1. So it's just if the update rate is 1 over t, then we just get z to the minus 1 doing that same substitution, that matched Z transform that I told you about. So big point, that's z to the minus 1. And phase is really important and gets overlooked often when we look at systems because we're used to seeing like a filter or something like that. Here's the magnitude response, and we don't look at phase, but it is a really important parameter to understand and keep track of. Okay, so now we're doing good. Control systems. We're going to get back to that. With that background in mind, here we have systems. So we're going to be covering the simpler world of linear, causal, time invariant systems. And that's going to cover many things, including allow us to go and branch to nonlinear and non-causal and other systems, understanding these things first. So we have H here as an arbitrary operator that's mapping the input to the output, right, as a transfer of the system. So we have some input system, that's the stimulus, and the system provides a response, right? Stimulus and response. And H is how we translate the input to the output. So generally we have the impulse response and the frequency response, and we'll be describing these systems either in Laplace as a continuous time system with the S-plane and the S parameters. I shouldn't say S parameters, using S, or the Z domain with the Z transfer function. So here, what do we see happening when we have an impulse? So an impulse function in time is all frequencies in the frequency domain. So that's the Fourier transform of an impulse. We're changing instantly fast. It takes all frequencies to do that. I discovered that as a tiny kid and teased my mom because I could broadcast on the radio and jam it by playing with a light switch on the wall, creating a little spark. So that's my poor mother realizing it was this. Not realizing it was this, but much later. It's like, okay, I could broadcast on the FM radio and tease her with that. So the impulse response. So we have an impulse. The system coughs out a response. If we took the Fourier transform of that, we're going to get the frequency response. We get the frequency response. We kind of see why, because when the impulse, if it's applying all frequencies at the input, right? And then we have what we should say is this relationship of the input to the output is convolution in the time domain. So convolution of the input with the output will predict the output. And in the frequency domain, it's multiplication. So if the impulse response is this, if we took the Fourier transform of it, it's showing us exactly what it would do to all frequencies as simply a product. Make sense? And here we can get to that we can take the Laplace and Z transforms, which gives us a lot more information we're going to see for use of the control systems. And then that gives us the system transfer function, H of S or H of Z, depending on if it's continuous or discrete. And if we want the frequency response, we substitute omega or e to the j omega for S or Z. All right, so on the S plane, we're setting it to the j omega axis. The Z plane, we're setting it to the unit circle. For that transfer function, we're getting the frequency response. So with that generic transfer function, we can get from those pole locations, we can determine stability. As I said, we can look and see if the poles are in the left half plane. We know the stability. If they get close to the j omega, the frequency axis, we can see things like ringing and overshoot, things like that. But generally, dynamics, impulse response, step response. And then also with this nice transfer function, if we restrict S to just be the j omega axis, as we saw before, we get the frequency response. So this is just to hammer home the idea of a system. So in this case, the system represented here is a filter. So a typical filter and different manifestations you may see of it in terms of analog filters shown here. So we could do a filter with an op amp or different types of implementations of filters. And here's a GPS filter, and here's a frequency response we might see. So here's the frequency going from DC to 6 gigahertz, and we see on a dB scale that everything's going to pass through in this narrow area right around 1.5 gigahertz where the GPS signal is, and rechecking it everywhere else. So that's showing us the transfer function and how it relates to the frequency response. Now, as far as the loop and how we're going to use it there, with the loop transfer function, we're going to take this complicated loop and decompose it down to or simplify it down to a 2-port network. That's going to be a filter just like we saw, right? And that's going to give us a lot of insights that you're going to see in terms of what we're going to do with that are important. So to develop the transfer function of the loop and the loop model, and there's going to be 2 different things. There's going to be an implementation model of how we would build it, and that might be what we would follow if we were doing a time sequence simulation point by point, like the more complicated one I showed you earlier here, tracking group, that showed us what the value was exactly at every sample. And we're keeping track of every sample exactly as we would have it in how they add together and what they do. Or the loop model that's going to be much simpler that we could represent by that equation that I showed you, right? And what we can do with that. So we're talking about how to implement that loop model. So the first thing is, for creating the loop model, we have to understand the transfer function of each element as we're using it in the loop model, and being very careful to keep track of units. So every block we're going to use in the loop model is going to have units at its input, units at its output, and some translation of that unit. It could be a fixed gain. In many cases, it's just a fixed gain. Or if that component is temporal or frequency dependent, if it's like a filter, then you're going to see S's or Z's show up depending on if it's continuous or discrete. So that's the difference. If it's a component that is instantaneous within where we care, within close to the loop bandwidth of what we're going to do and what we're doing, if it's instantaneous, then we can treat it as a fixed gain and it's a unit translator. You're going to see that. But if it's not instantaneous, if it has a response time within our time of observation, then you're going to see S's and Z's show up as part of that component. So here's a VCO. So with VCO units, we could voltage-controlled oscillator. We put a voltage at the input, we get a sinusoidal frequency coming out that we can vary as we vary that voltage. So we could pick units at the output, we can pick units of volts. And so we would see as we sweep our control voltage, from a small to large number, we're going to see our output. This is a chirp. It's increasing in frequency, right? So we could pick units of volts, or without changing the component, we could pick units of hertz. So what's our vertical axis going to be? If our vertical axis is hertz, frequency in hertz, we're seeing what's called instantaneous frequency, right? Or we could pick units of phase, right? And so then we get this exponential in terms of, frequency is the derivative of phase. So you're seeing that relationship here in terms of it as an increasing slope as we go forward in time, right? So we can pick whatever units we use. The units we pick depend on the type of loop we have. We're going to make that convenient for the loop implementation. And specifically, and often it starts with the discriminator, like it said before, right? And we really want to find the linear models of what we could use. You're going to see why in terms of the implementation of the loop. So if we were going to use this VCO in a frequency lock loop, then this middle one would be the best choice, right? Because it's linear, would respond to frequency. If we're going to use it in a phase lock loop, we would use that last one there, and I'll show you how to linearize it. If the discriminator is a phase detector, we want units in radians. If it's a frequency detector, we want our units in hertz. So this shows the transfer function of the VCO if we were working in units of hertz. So this is what I mean when we're going to take that block and we're going to convert it to a transfer function. And in this case, we're going to assume that VCO is so fast when we change it, the frequency immediately changes compared to the loop we might be working with. So imagine we have some very slow loop, and I adjust it, and it's instantaneous from sample to sample, and it changes. So in that case, all we're interested in is this slope. So here we have a control voltage, and we get this right off the data sheet for the component. We have a control voltage, we have an output frequency, and that we would call a gain. It's kV, hertz per volt. It's translating volts to hertz. So you could think of it as a simple block like an amplifier that has gain, but it's also converting units. So we're putting in volts here, and it's changing the frequency directly here. So when I said look at waveforms versus time, and it can be anything, well, this is frequency versus time, which is a little confusing, but we're saying instantaneous frequency versus time. And as a waveform, we're able to control it like an FM modulator. We can control the frequency versus time directly, and that's where we would use kV. Now, a little confusing because an integral shows up, but the takeaway is what I said before, that phase is the integral of frequency. I explain it better the other way, that frequency is the derivative of phase, and you can just clearly see it as delta phi over a change in phase over change in time. And if we go back to the whole spinning phasor and the bicycle wheel, right? E to the j omega t, you see it there. If that bicycle wheel is spinning at a constant rate, that's a constant frequency. The phase versus time is changing at a constant rate. It's a phase ramp would be a constant frequency, right? So another good takeaway when you work with Laplace, this one's worth memorizing, is that the Laplace transform of an integral, of an integration, is 1 over s in the Laplace domain. So that's what's so great about Laplace, by the way. We could reduce differential integral equations to simple algebra, right? So here on the left, if you stay in a time domain, we got to do integrations and stuff like that. If we convert it to Laplace, and we know the Laplace transform of this function, and we're just dividing by s, that's simple algebra. That's a big motivation for using this. It makes our life easier. So we're going to be making this loop model that's going to be, if it's an analog loop, we're going to create this transfer function. That's that h of s function. It's a function in Laplace, and we're going to be doing that. So this component, where it was just kV before, if we said, no, we're interested in phase versus time, not frequency, because our detector, our discriminator, is going to be a phase detector. It's going to respond proportionally to a phase difference, not to a frequency difference. We use that component, then it is a phase-locked loop. And in that case, our model of the VCO has to be in units of phase to go into that phase detector. It's in the loop model. It doesn't change the implementation. It's just in the loop model, right? So in that case, we would have volts coming in, and we would have this kV, that's the slope, but we divide by s because it's integrating the frequency. So you already figured out what kV was, frequency versus time. Want to integrate it in Laplace, just divide it by s. So that's why you see this kV over s. Don't confuse it with seconds. S is our friend from the Laplace transform, right, of all the possible spinning phasors growing and decaying. Ultimately, we're getting every block in here as a function of s, like we would do as a function of z, if that block has a temporal characteristic or a frequency-dependent characteristic, and it has to have s and z's in it. Okay, so that would be what we're seeing, which is cool, is that this is a low-pass filter. When it's in units of phase, the VCO is a low-pass filter. You're seeing the S in a denominator. And what's its frequency response? Just replace S with j omega. J omega, you just replace it with frequency. So it's going 1 over F, right? It's a low-pass filter going down as the frequency doubles, the magnitude of the output goes in half. So it's 6 dB per octave, low-pass filter. Octave is doubling in frequency. And I was talking about the magnitudes, if you're converting to dB, 20 log, so that's the shortcut to what I just did really quickly. Or, if you go a decade, if it goes up by 10, then 20 log of 1/10 is 20 dB, so it's 20 dB per decade. So it's a filter that's going off 20 dB per decade or 6 dB per octave. The VCO. The same VCO, then the frequency lock loop wasn't a filter. Depends on the loop. So here's a phase lock loop that we'll see implemented. And again, keep track of units. So we're seeing in the components, here's the VCO, and it's converting voltage to phase as a phase detector was used. So we're putting it in units of phase, and 1/S radians per volt, volts to phase. And then we have a divider, or would represent a gain, and is converting radians to radians. So it has phase in and phase out. And if it was a frequency divider also divides phase. Divide the frequency in half, you cut the phase in half. Go back to the spinning phasor and see exactly how that works. If you double the frequency, you double the phase. And even go e to the j omega t, put a phase term, square it as a frequency doubler, and you see the factor of 2. So it's radians as units of phase, radians as units of phase. We have something that's a phase detector, and we've convinced ourselves this phase detector is going to give us a proportional voltage based on a difference of the phase at the input. In implementation, we're still providing two real sine waves or whatever we're doing. We're getting a phase difference at the output, but in the model, we're just going directly to the units of interest. Right? And then we'll have our loop filter. In this case, a loop filter, its units of at the input is volts, its units of the output is volts. So that's important. Each of these blocks, the units have to match, and then we'll be successful in terms of doing that. And once we do, your goal is to get to this open loop gain, and with it, we can then use all the tools to give the responses and things like that we had. So the open loop gain, this open loop gain is going around the whole loop and assuming negative feedback. So the loop is going to be assuming negative feedback to keep it stable. The idea there is if we have an input, we have an output. If we're feeding our output back into the input, if it's negative, we're going to be stable unless we feed back too large of a value, or you'll see some stuff with the stability after, how that affects it. But this open loop gain is assuming the negative is there, so you don't count it. And you're just going around inside the loop and multiplying these different gains that we derived together. And that's giving you the open loop gain. And ultimately on this page, you're seeing this relationship, which is great because it holds everywhere, of the closed loop gain. Closed loop gain is going to give us the two-port network that this complicated internal thing ends up being. It's just a simple two-port filter as a closed loop gain. And it's going to be the forward gain over 1 plus the open loop gain. That denominator is called the characteristic equation. Come across that, characterizing the whole loop. So if you're successful in getting the open loop gain, then you can, from any input to any output, determine the closed loop gain, which is great. So this is showing us there's the characteristic equation. The roots of that are going to be the roots of this whole thing are going to be the poles of this closed loop system. They're in the denominator. The poles are the roots of the denominator. We can look at that directly to see if the system's stable and where those poles are and move them around and all that stuff. So we can manipulate everything from the denominator directly. And then we have the forward gain that we can, as I mentioned, we can choose any input to any output. So in this case, the input was here to the output. But you'll see, in the examples we'll see examples where, we can have an input right here, such as we saw a VCO. It could be the VCO phase noise, modeled as noise coming in on an output node. And what is this two-port system as a response to the phase noise and how it cleans it up and all that kind of stuff we'll see. So it's great for doing all that. And stability from that open loop gain, from that same open loop gain, the Bode stability method, which is applicable as long as the system you had before you created a loop was stable. The system itself is not stable, such that we can't even measure the open loop gain. Then you have to do a Nyquist stability plot, which we're not going to talk about. But as long as your system is stable to start with and you can go and measure the open loop gain, this is great because we don't even have to know anything about the system. We can just go in the lab or go into our simulation and create this plot if it's stable. Just come in from one node, look at the output, and figure out what is its magnitude and phase as we sweep frequency. So we don't have to do any math. We could just go right to our system if we have our hands on it, meaning if the simulations aren't done or if it's working down the lab, right down there and get this Bode plot. Which, by the way, we can then model and figure out for transcendental systems, which may not come to simple poles and zeros, things like that. We can figure out the same stability, like time delays, for example.
Forward gains.
No, good question. The forward gain is specifically from some input to some output. So in this case, the forward gain would be KF times the loop filter times the plant, and it wouldn't include KR. Just from this input to this output, just multiply those together as each block is an H of S. Just put the product.
Right, I'm just trying to map it onto my physical, like empirical experience. So that would model how much the signal is like amplified or attenuated.
Yeah, depending on what these components do. So if we break the loop here and we just say, hey, here's the input and here's how it acts at the output. So that could be anything. It could be a simple amplifier with a gain of 10 and the forward gain would be 10.
But it could have a frequency phase.
That's right. If any of those blocks in the forward gain path have an S if it's continuous or a Z in them, then it's frequency dependent, and then we have to be careful. And if I was in there modeling that system down in the lab, I would look at things like the step response to get that temporal relationship. If it didn't, if I saw it was instant, and really what you have to do is everything has poles in it. You don't want to deal with million poles if you're dealing with a low pass system and these poles I'm talking about are 100 times higher frequency, we can ignore them. It's good to be able to recognize and do as we simplify the system to its most basic form. Yeah.
So what it's a rule for outside the range of care.
It could be anywhere from 10x to 50x, depending on how sensitive we are. But I start with like when I make control loops, I look to find, the worst thing is sticking some arbitrary filter inside your loop. Better way that it's competing with your loop bandwidth, right? Like putting an FIR filter in your loop that has a large delay is a bad idea. Let the loop filter itself clear the signal. So if any system that I would put inside the loop, I want it to be 10 times higher in terms of that. So I could use FIR filter or some filter to get rid of some high frequency components. But I look at what's the loop bandwidth we're going to do, and I don't go anywhere below 10. And now it's only affecting it very slightly. The 100x will have no effect at all. It's like on that order. But if you start competing with it, now it's part of your loop, and you got to consider it in this stuff in terms of what it does, which, I have a high order loop. So this is showing you what I want you to see here. This is what do you need to know about the Bode plot? The Bode idea is the magnitude and phase versus frequency. If this phase shifted more than 180 degrees by the time the gain is still positive, now you got positive reinforcing feedback. So here at this point, what I want you to see is the idea of the Bode stability criteria, that if this magnitude is 0 dB, which is gain of 1, or lower by the time the phase passes 180 degrees, then that would be stable. Kind of makes sense, right? We have gain, and we have 180 degrees of feedback and positive gain, and that's reinforcing and having something glow be unstable. We're doing all right on time. You guys still awake? 52 slides. We'll take a 5-minute break, and then I'll show you the Python for those of you that want to see the Python. And if you don't come back, I won't hurt my feelings. So this is the Bode stability criteria. This is a good takeaway. You're going to see us work with that in terms of what it is. And ultimately, when this crosses 0 dB, the amount of phase we have from that critical point is called the phase margin. Phase margin. And if we have low phase margin, then we'll get these underdamped conditions a lot, bringing uncomfortably close to going unstable if we have variations in parameters, things like that. We like to have phase margin. Gain margin is when we cross 180 degrees and we go up here, how much did the gain attenuate? So you get both parameters, phase and gain margin. You can read it from the plot. So here, in terms of the benefit, being able to make the loop model and come in and out as any node and predict the total noise of the output from all your sources. It's great for that. This is an example, we won't go through in full detail, but this is a fractional N delta sigma modulator frequency synthesizer where you can have a loop model and you have many noise sources. That's what these are showing, is the transfer function of each possible noise source. Like the VCO would be its phase noise. This SDM is the delta sigma modulator, what its noise is, going from the node into this node here as a noise source, going to our output at the VCO output. So you have several opportunities of injecting inputs, and you can do that with this approach as noise models. You could say, hey, I have a power supply noise that gets into here, and you can inject that into the loop filter, the active loop filter. Figure out how clean does it need to be, because the output is going to be the composite of all these noise sources that we're seeing versus frequency. So they're a result of a bunch of two-port transfer functions. Every one of those inputs could be outputs. And Thatcher used a different forward gain. What's the forward gain from this node into the loop to the output? We can do that with the loop model that we described. That makes sense? The important takeaway of how practical having the loop model early on is in terms of specifying what each of these components need to be in terms of their noise performance and stuff like that for a target response that we may describe in frequency, such as this is the composite phase noise.
So that total response is the sum of all of them?
Yes, the sum of each individual two-port response as a noise. Yeah, that's right. And each one of these if the VCO was the only noisy thing in here, then our phase noise as limited by the VCO would be on this line here. Isn't that cool? Here's the reference, right? Here's the reference where our noise out here, and this is why we use the synthesizer. The reference noise is going to dominate the noise that's out here, and it's much better than the VCO. You're seeing the VCO after the PLL, not before. But if you looked at the VCO on its own, it's going to be way out here and much worse. That's why we're using the PLL. Okay, so analog PLL. Here's an actual example we'll walk through. As if you were on the bench, we're mapping out this thing. We want to buy components and build this integer N phase lock loop. It's relatively simple. We have a 100 megahertz reference oscillator. We have so I work for Microchip, so I got to throw in one of our parts. I'm not here representing Microchip, but I always like to throw in something from my employer. So it's a Microchip phase frequency detector. It has the counter. So a counter is a frequency divider. We want to divide by 100, count to 100, and then tick. Count to 100, and then tick. So counter is a frequency divider. So it has an integer counter that we can program between 100 and 200. It has a phase detector that's going to do exactly what I described. This is an analog system. So when this frequency coming in, that could be anywhere from 10 gigahertz to 20 gigahertz with an ADI part. Anyone from ADI here? Anyone from ADI? So I used to be from ADI. So I like to give a plug to my past employer. I used to be with Hittite. So this was a Hittite part. So an HNC, Hittite part, VCO, very nice VCO that can go anywhere from 10 gigahertz to 20 gigahertz. And we're going to use it to create an integer end phase lock loop. So we can produce any output frequency from 10 gigahertz to 220 gigahertz in 100 megahertz steps. Make sense? So this is the eval board for the phase frequency detector. And it can work up to 40 gigahertz. It has programmable integer dividers on both the reference port and the feedback port. So it's pretty flexible in terms of what it can implement. And a 8 gigahertz phase frequency detector. So it works up to 8 gigahertz here. So we can divide down whatever frequency we have to be 8 gigahertz or lower in terms of our phase detection. And then it has charge pumps, which are basically going to convert the current outputs of the phase frequency detector or convert it to currents proportional to the phase difference that we have at the input. So it's giving us an output value that's proportional to the phase error of the input. And the VCO, this is what it looks like, is a little chip. And we have these two things we've grabbed from the data sheet. We're looking for, hey, what's its tuning sensitivity? So as we tune it, what's its output frequency doing, right? And then we want to look at what is its phase noise, because we're doing this whole thing we're locking it to something to clean up its phase noise rather than run it open loop. So we have a phase noise, and phase noise in simple terms is, if you have a pure output frequency and the phase isn't changing, there's no phase error, then it's the cleanest thing in the world, there's no phase noise. If the phase versus time is modulating, right? We saw how we can look at its frequency versus time or phase versus time. So if that phase is modulating versus time, so if I had phase that was modulating at if that says 10 kilohertz, yeah. So 10 kilohertz minus 70 dB C per hertz. So minus 70 dBc per hertz at 10 kilohertz. If I took that slice with a tight filter, 1 hertz wide, and I looked at the output as a phase, output of the phase detector, I would see phase going back and forth sinusoidally roughly at a 10 kilohertz rate. So that's the phase modulation. And it would be really small. It would be 70 dB down. And then the higher frequency phase components are 80 dB or 90 dB, et cetera. So it's showing you components of each individual phase modulation that's occurring at it. And that's a method of evaluating the ways of this voltage control oscillator, VCO. So the PLL loop model, so here's the loop model where we have KV over S, as we said. We have a divide by N because we're dividing. We have a phase detector, and we have our loop filter. I'm talking about that, right? And so now we are going to break it into the individual components for that loop model. So we look at the data sheet, and here's our frequency versus tuning voltage. And conveniently, for us in this particular data sheet, they did provide the sensitivity versus tuning voltage. That's the slope. That's what we want. We wanted the slope to derive KV. And what you're also seeing is the slope isn't completely linear, right? So depending where we operate, that slope is going to change. That's important to notice because you're going to see how that slope drives the loop bandwidth. That means we're going to have different loop bandwidths depending where we operate, different stability, etc. And what I'll typically try to do in a loop, especially easy if it's a software loop, is to linearize the component right at its source. Because if we make that linear, then we're fixing it from cross dependencies of other changes later, right at the point and keeping it very linear. Linear is good, and we get the same result no matter where we operate, rather than having something far away actually. So I would have an abstraction right there that would take this and fix it through a lookup table or whatever to be linear if I care. But here it tells us how sensitive we would, depending if we operate here or if we operate down here. We're seeing tuning sensitivities vary from 200 to 700. So I would either linearize it or check my loop model and put in both corner cases to see how I operate in both ends. But in this case, we're starting with, I said I want to go from 10 gigahertz to 20 gigahertz. So what I'm going to show you here is say, let's start at the midpoint. So we're operating at the midpoint. So we look at that, 15 gigahertz is a control voltage of 7.5 approximately, right? And so then I look over here and the slope, they did it for us. The slope right at that point, at that inflection, is 600 millivolts per hertz. That's in millivolts. 600 millivolts per hertz. So, so 15 gigahertz slope is 600 megahertz per volt. 600 megahertz per volt. Sorry, I said that wrong. 600 megahertz per volt. So at this operating point, in terms of kV, in terms of radians, 2 pi f makes it radians. 2 pi f, so kV is 2 pi times 600 megahertz per volt. So that's our number. We determined kV. And because we want it in units of phase, it's going to be divided by S. So its block, kV over S, has a kV of 2 pi times 600. Any question on that? Pretty straightforward. Similarly, the phase detector, you look on a data sheet for the phase detector. Here we have possible phase errors at the input and what its output would be. And we got KPD, the phase detector gain, of 120 millivolts per radian. These are the numbers we want, and you see how I'm keeping units the same. Radians, 2 pi f per ECO, and we have radians here in terms of what its phase versus sensitivity would be, and we get that right out of the data sheet. Just have to be careful that the units match. And then here's the op amp that's actually on the eval board as a differential op amp, and if you follow the circuit equations for an op amp, which we don't have to do here, what I want you to see is we're going to get this transfer function of 1 plus S tau 2 over S tau 1. 1 plus S tau 2 over S tau 1. So some things to notice in this right away is this transfer function has a 0 where? A 0. Meaning the 0 is where the transfer function, you put in the value of S that makes the transfer function go to 0. As opposed to the pole is a value of S you put in that makes the transfer function go to infinity. So right here, this circuit, this little block that we have that's described by this equation, that's what we're looking for. We've converted it volts to volts with this equation. This is something that's sensitive to frequency. That's why the S shows up. And it has a pole at S equals minus 1 over tau 2. And it has I'm sorry, did I say pole? I'm getting tired. It has a 0. It has a 0 where the numerator, if S was minus 1 over tau 2, this numerator would go to 0. Where is the pole? Where is the pole? What makes this whole thing go to infinity? S is 0. So if I plug in 0 for S, 1 over 0 makes the whole thing go to infinity. That's the pole. There's a pole right at the origin, which, by the way, is the telltale sign of an integrator. You put in DC, it's just going to grow to infinity. And that's what this is. So if I break it into, if I just do some math, simple math here, where I break it into two forms, we have 1 over S times 1 over tau 1. Remember I said before, 1 over S is the loss of an integrator. So we have an integrator with a gain of 1 over tau 1. So tau 1 sets our integration gain, and we have a proportional path that's tau 2 over tau 1. So you see this I and P as being the integral proportion term of the loop filter. This is a PI filter. It's very common to see, especially with a PLL with a VCO like we saw. It has a proportional integral term. You might also see a differential term, PID, things like that. EI, and we see the components. What we do are to see how they relate to, and I used tau 2 as R2 times C1, and tau 1 was R1 times C1 for the time constant C. Get some water as a stir at my equation. Any question on that? besides the circuit that we're not going to talk about? Okay. So PI loop filter. Taking the same thing here as 1 plus S tau 2, S tau 1, putting it into a block diagram, you'll see the same thing in digital block diagrams where we have an integrator, which is an accumulator, with some gain, which is our tau 1 as the integral gain, and then a proportional path that goes around, multiplied by tau 2 over tau 1 is a proportional gain. So now that we have the blocks, this is where you see getting the open loop gain. We can talk about the forward gain again. So you take each of these blocks, and we're just going around the loop. The negative is implied, so we don't count the negative twice. And our open loop gain is going to be kV over S, right, divided by N times KPD times our loop filter, H of S. So there we're seeing the whole thing. This is the equation of that PLL. Clear? That's the open loop gain. That's the open loop gain. And that's I'm going to go through the digital one, and we'll see how we use the open loop gain with it.
Yeah, so it's a filter that's usually either PI or PID.
It can be anything, because we can go into higher order loops. It could be we could have a loop filter that's just a proportional, which may not be a good idea, but we can have that. It can be just an integral, which wouldn't work in this one, go unstable. But we can have other loops where if it was a frequency lock loop and we didn't have, notice we have two integrators in here. We have the integrator and the loop filter. We have an integrator and a VCO because of the units we use, that 1 over S. We're making a frequency lock loop, and we could get away with the loop filter just being an integrator as a first order loop. Here, we could get away with the loop filter just being proportional and using the integrator that's in the VCO as a first order loop. So it depends on what type of loop we're making and the dynamics of it. And I show some stuff in the backup slides. You can download all this stuff from the schedule, by the way. Presentation, there's stuff in the backup slides that talks about it, things like that. Let's go through a digital PLL just to show what you're going to do is you're going to see the same thing just now in the digital domain. So the stuff I said about S going to the Z will come into play here. And here is one that is demoed in the notebook where we have this is an FM broadcast signal that has a pilot at 32 kilohertz. And we're going to use an all digital PLL to lock onto that pilot signal. So what we see, and what I want to have be familiar to you here, is we're seeing some input signal. So before I call it a clean reference, in this case, 10^30 reference, Freddie, coming in. The multiplier is a way to make a phase detector. Multiplier is a way to make a phase detector. You multiply in frequency, it adds and subtracts. The difference will be the phase itself. So you can, by the way, you can use an XOR gate as a phase detector. An XOR gate's a multiplier of two square waves. XOR gate each nice phase detector. If you're stuck needing one without a lot of stuff. But a simple multiplier is a phase detector. And then you're seeing, and this block diagram is the implementation. It's the implementation. So we have the loop filter, and do you recognize there's the accumulator. So this is an accumulator. The zeta minus 1 is unit delay, and our output is going to be the next input with the previous output. It's just going to grow. It's an accumulator. And then we see the proportional path coming around, and we have a gain constant tau 2 over tau 1. We have a gain constant here, 1 over tau 1. We're seeing P and I. There's a parasitic delay just in terms of our loop. We can't apply the next output until the next clock cycle, so it ends up being a parasitic delay that if you don't include in your model, you'll not get the results that you're expecting. So that's what that is. And then here's another accumulator, right? Here's another accumulator where it's taking the output after a registered delay, and that was in a particular implementation, similar reasons. This is a numerically controlled oscillator, an NCO. An NCO is simply an accumulator followed by a lookup table. So it's the digital counterpart of the VCO. So we have an input that's a digital word right here. And as we vary that input, we can get different frequencies coming out. Because the accumulator is an integrator, so it's converting a frequency control word to a phase control word, all right? The phase is the integration of frequency, right? Or frequency is the derivative of phase, vice versa. So we have a frequency control word. Imagine if I put in just a digital value of 1, and this is a counter, an accumulator. It would grow on each clock cycle by 1 value, right? And then imagine I took, this is showing me taking just the MSBs of that. So this can have very high precision. We'll just take the most significant bits. Eventually, we will count through that lookup table, which will generate the sine wave at the output. So that lookup table is just giving you the trigonometric operation. Tell me the sine of that phase work, right? So the faster we count, the faster the sine wave is going to go, and it keeps cycling on itself. So we get a continuous sine. You can see if I count by 2, it's going to go twice as fast. If I put a 3 here, it'll go 3 times as fast. So it's a numerically controlled oscillator, forcing identical to the solid electrode. Make sense? As a block, I'm showing you something that will work just like the VCO, where we can change the digital value, and it will produce faster or slower sine waves depending on that value directly. It's going to be directly proportional, frequency of it, directly proportional to the value of that input. So that's showing you those 3 components. And the digital loop model, same thing we did before, except what you're seeing here, like we put the S in the denominator before. Remember I said the origin on the S plane is Z equals 1, the Z plane. So that has a pole as Z equals 1. That denominator goes to 0, the pole is equals 1. So 1 over S, the integrator in Laplace, has a pole at S equals 0. The pole is right at the origin. So you map it over to Z, right at Z equals 1. So that's doing the same thing you saw before. This is going to be dependent on Z as a frequency variable, and we have KPD. And the numerically controlled oscillator, if you work it out in what I described, here's the frequency control word that's going from, all zeros up to its total width, how many bits we have at the input of it. And it's going to put an output in frequency that goes from DC to half the sampling rate. So the pi is representing normalized frequency. If you divide the frequency axis on your digital by the sampling rate, then your digital frequencies are going from 0 to 1, Fs being the sampling rate. If I divide by the sampling rate, Fs over Fs is 1. So you'll see frequency axes in a digital domain going from 0 to 0.5, representing DC, the Nyquist half the sampling. So similarly, if we want to talk in radians per second, radians per sample instead, you'll see 2 pi f times the frequency. So if sampling rate was 1, it would be 2 pi times 1. So you're seeing it go from 0 to pi radians per sample. That's what's going on with that. So it's just the frequency. So our frequency can go from 0 to pi, and so that's going to be kV. kV is going to be pi over this total range. That's the slope of that. And we divide by Z minus 1, get that integration. The multiplier is a phase detector. So this is showing you what I described earlier. If you take a multiplier and if you just think of cosines, if I go omega 1 of t plus some phase, and cosine omega 1 of t, we get the sum and difference. We multiply to cosine. The sum and difference. So this high frequency component would be double the frequency plus the phase difference. And then the low frequency component is the difference. The difference of these frequencies would just be the phase itself. The high frequency component is going to be removed by our loop filter, or we could have an additional high frequency filter to get rid of that. It could be a much higher frequency, but ultimately it's going to be, and with some, so I scaled it so we don't have the A squared in my implementation. So it's going to be directly A cosine of theta. So it's an output that's proportional to the phase. So if I plotted phase on one axis, I have some output that's proportional to the phase. And if you zoom in here at this particular operating point, we get this nice linear response. Remember I said we want a linear response? So it's saying when this loop locks, we're going to lock to where the error is 0. The error is 0, and the phase will be minus pi over 2. We'll pay attention to this slope. The slope is positive. The slope is positive here. We could also use it in a loop where if we change the feedback, or if we have the feedback the wrong way with the sign, it could lock to here, right? And then our phase slope is negative, but we still have the same gain. We just have a negative slope. Slope is our D. So now we have KPD. This is the phase detector gain. So it's, again, just keeping track of units, being careful with units, you get the right values. That's the bulk of the work in making these loop models. Extracting these things. What do they do? When I change the input, how does the output change? And again, is that output have any dependence on frequency? Anywhere near where we're operating? No. If it's instantaneous like this is, then it's just a simple gain, the slope of that transfer function. Phase going to magnitude. That phase error here, I have a magnitude coming out. And then the loop filter, well, this is cool in the sense of you're seeing the same block diagram I showed you before. And if we work this all out, which is just some math of all these nodes and adding and subtracting, we're getting this nice transfer function. And I grouped it together as tau 2z plus some constant, depending on tau 2 over tau 1. In terms of that. So I have transfer function in different forms. I could have it shown as the proportional and the integral relation, or as one combined transfer function. We like the combined transfer function because ultimately I want to get the open loop gain and I want to make that as simple as possible. And if I can describe that as polynomials of z, we'll be able to use these tools directly. Which is what I did here. So it looks like a lot of math, but I just took each of those components we described. There's our kV over z minus 1, which is the numerically controlled oscillator, times KPD, which is our phase detector, times h of z, which was the loop filter that we used. I'm putting it all together, and I put it in this clean form where I pulled out the gain and the poles and zeros, right? I have z by itself, so I can identify where the poles and zeros are, which is helpful when we start working poles and zeros, optimizing the loop filter. So that's the open loop gain with that. Any questions about that? So what we're going to do next. So this is the presentation part. We'll give you a 5-minute break and a chance to escape. And for those that come back, we'll fire up Python and you'll see, okay, how do we work that into the control library? So what I will show you, I'll bring that up when we start. Yeah, because I have the simulation demonstration. So I'll show you a little bit of this control library, but we're using this library specifically, and we're going to see, okay, great. If I have this open loop gain that we did all this work to get together, what can I do with it? What does it mean? And how easy is it to use with the tools in terms of seeing the cool things we showed initially, like the loop bandwidth and the time responses and the things where I showed you that we predicted the actual response of that carrier tracking loop. Boom. And then if you don't come back, but you still want more DSP from me, I'm just highlighting these. These are the courses I teach through IEEE Boston or dsprelated.com. So there's 3 courses I have now that I'm always going through, cycling on those 2 websites, so you can go there for more. A lot of the control loop content is in a course called DSP for software radio. That's not even listed here. It's actually happening right now. And then DSP for wireless communications is more from the ground up in terms of looking at, with more time with me to really understand the Fourier, Laplace, and Z transform and how we build that up into very high performance filters and multi-rate signal processing and the FFT and things like that. The DSP for software radio is now top down where, hey, let's implement carrier tracking loops. Let's go through a QAM modem. Let's build it in that simulation and timing recovery and AGCs and all the things you would see in the software radio with the loop models and the benefit of the loop models. And importantly, in that one, understanding, this is my both analog and digital background, understanding how we use DSP to cooperate with or compensate for the analog realities that we get, such as phase noise and quadrature imbalance and amplitude imbalance and channel distortions and all that stuff. So as equalizers, all those things are in that Keepers Software Radio course. And then if you want to get into Python, then there's a whole Python course that just gets you up to speed in Python for simulation and modeling as we're doing here. So with that, 5-minute break. Well, I'll change this over. I'm going to sit over there, and then we'll fire up the Python together if you want to see that. And again, everything we're showing, everything we have, this presentation, it's downloadable from the calendar. So you can grab a copy of that there.